negative field is when there is a scalar potential, right? So now look at this one. It tells you to find work done by this vector field. The vector field is this. The gradient of the, what potential function? It's the gradient of, and it's two variables of that function, right? Now, my question is, should I take the gradient to find a field? No, field doesn't matter. The potential matters because I'm trying to find the work done. Work done means, so one, work done equal to vector line integral. Two, potential is given. Therefore, use it. Don't worry about the vector field. If the potential is given, why would I even bother? Line integral, use the potential. If you have a potential, so the entire story of the line integrals that we do all that work is because some vector fields don't have the scalar potential. When they have the scalar potential, it's very essential to us. So basically, when you, in physics, in many areas of the physics, you can break down fields into fields that have scalar potentials and fields that have vector potentials and compute things easier. And that's the beauty of it. Like electromagnetism, you see it a lot in physics, you see it a lot in a lot of aerodynamics, fluid mechanics, that sort of things. You see it a lot. So that's the thing. So we give you the basics, you see them there for real. But then before going there, what I suggest is that have a feeling of it, have feeling of everything that is happening in Calculus 3, basically. Because it's very, it follows a very natural way of life, basically. It's not, it looks very complicated, but it's not. That's the thing about Calculus 3. So what am I'm computing this one. Sorry, I kind of lost track. I suddenly started just, you know, there are people that in the middle of nothing, they start singing. Every once in a while, I start singing, basically. That's what happens. Okay, so now here, find the work done by the gradient vector counterclockwise. Counterclockwise, there's a circle given to me. It goes from 2 to 0 to 0 to 1, negative 2, sorry. So here, 0, well, 2 to 2 and 0 here. And it goes not here, but here. Am I right? Down there. So that's the path, and it's counterclockwise. Counterclockwise for circles is always good. The natural way of parameterization is there. And then what do? So I parameterize. Or do I need to parameterize? No, I don't need to parameterize. Why do I not need to parameterize? Because I said there is a potential. So I can skip the entire story and go to the last page. And last page tells me that the vector line integral of this thing over this C the vector line integral, is just going to be f evaluated at 0 and -2 minus f evaluated at 2 and 0. That's all. Don't even bother. You can do the other method also. You can just take the vector line integral. But why? In this case, you can. Some cases it becomes excruciating painful. This one is mildly, it involves a mild amount of work. But sometimes if you go through parameterization when there is a potential, it's going to be excruciating pain involved with it. So don't put that on you. So when there is an easy way, go with the easy way. That's what I'm trying to say. I don't know if I'm saying it right. Talking about excruciating pain. Do you guys want to hear a joke? Not very funny, but okay, so I'm trying to, in the beginning of the semester, I usually remind freshmen that we have all sort of tutoring available at KU, right? Free tutoring is available. So, and I'm trying to type a lot of stuff, and this is fall semester. And I type, instead of tutoring, in 3 places, I type torturing. I could not shake that off. It was just staying with me the rest of the semester. Did not work very well. So I have here, I have 4 minus 4, which is going to be 0. Yep, do not make that error. If you are. Everybody okay? So this problem gave you the potential. It didn't even talk about the vector field itself. And you just use the potential. You didn't even care about the vector field. Now let's care about the vector field when we are suspecting that it's conservative. So how do I find the potential? How much time do I have? Am I going too slow? No, I think I can make it. Yeah, so. Now, let's say this is the vector field. And the first question is asking, is this thing conservative? So I have to figure out if this is conservative. What do I do? Conservative fields. Oh, by the way, is there a hole for this, for the domain of F? Is there a hole? Is there any place that domain is not defined? Cosine of z is defined everywhere for all reals. -1 is a constant defined everywhere. Negative x sine of z defined everywhere. No. So that checks out. After that checks out, then I can think about, because if that doesn't check out and I'm not excluding the whole, I'm going to be in a problematic situation. So the second part, I'm going to check the curl of the F. And curl of F, curl of gradient vectors are supposed to be basically 0, right? So I have to check that. So I go I, J, K, partial X, partial Y, partial respect to Z, cosine Z, -1, negative X sine Z. And then I compute. So it would be I, and I have partial respect to Y of that thing, which is 0, partial with respect to Z of the constant, which is 0, so 0. Then J is going to be negative of that, which is going to be positive sine of Z minus that partial minus, wait, hold on. That was that was the negative. A negative sign comes in, and that's right. And then I have minus, 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 and that would be minus on this. Okay, so now k is derivative of -1, which is 0, and partial of y, partial with respect to y of the cosine of z, which is 0. I do have 0 vector. That one checks out. Both conditions checked out. Now, if I use that method that I told you about taking antiderivatives, it's going to work out. Before that, I didn't know. When I know it's conservative, that method works. Otherwise, you don't know, right? So that's the important thing to know. Now, you guys are ready? That was the first part. Now, what do I mean by find the scalar potential? What do I mean by taking antiderivative? So what do I have? I have this whole thing. And then what I'm doing is taking the integral of the first one with respect to x, because that's the x component of f with respect to x. And then taking the y component of f with respect to y, taking z component with respect to z. Why? Because I'm claiming, if this is conservative, I'm claiming the first term is partial respect to x, the second term is partial respect to y, and the third term is partial respect to z. I'm just undoing those partials by taking antiderivative with respect to whatever it is, basically. Questions? No, all good? So now that I'm taking the antiderivative, I get x cosine of z plus a constant of the other variables. A constant of y and z. This one I get -y plus a constant of x and z. And that one is just with respect to z. So x is a constant. The negative sign is the negative cosine. No, positive cosine. Antiderivative x cosine of z plus c. Oh, this is c2. c3 of x and y. Now what you do, you go and find the common terms. That's a common term, right? Why is it not showing in here? Oh, because it's just function of x and z, and that's just constant for that one. So that's okay. Write down the common term, and then in your head, just scratch it out. Don't go after it again. One time, write it one time and don't scratch it out. Then find whatever is there. Right now, I only have -y. So I write the -y. Before writing the -y, make sure why did it not show up here? Because, oh, this is a constant here. Why did it not show up there? Because it's a constant there. And then you can add a c if you want to. Any constant, actual constant is okay. Now that you have found these, I think the next question, part C, is going to ask you to find the line integral. So line integral, it's asking you to find the line integral. Well, it gives you parameterization. Oh, do I even care about the parameterization? Field, conservative, no one cares about parameterization. Nobody cares about your cow? You guys play Minecraft? No? Okay. Yeah, there's a big Minecraft gamer They keep saying, nobody cares about you, cow. No, you never heard of that? Oh, it's been a while, I think. I think he's not famous anymore. But in the beginning, when Minecraft came over, he was very famous. So I don't know. It's one of those things that stuck to my head because I felt bad for the cow. And so nobody really cares. That's a property. The fact that parameterization doesn't matter is the property that is called path independent. So it doesn't matter where parameterization doesn't matter. Path does not matter. That's the thing. So it's path independence. That's what we're saying when we're saying path independence. And so you can see the next problem, I'm sorry. But it goes from this point to that point. All I need to do is I compute the beginning point and end point. So I compute f in the beginning, the end point and beginning point. So the integral f dot dr is going to be, f at e to the pi, e 2 pi and pi minus f1, 1 and 0. And so what is that? So see, it would have been a huge mess if you parameterized it. And the integration would have been too difficult. Now here it's just e to the pi cosine of pi minus e to the 1 cosine of 0.